Yeah, just to keep things moving. And yeah, the next presentation is self-evolving MCPs.
Hi, hello everyone. My name is Wanda Ho. I'm from Eden Code Incorporated, and here is my teammate. We have Miao Li from Georgia Tech and Hongye Hu from Harvard and Eden Code Incorporated. Today, I would like to focus more on a framework of self-evolving the MCP for scientific Python libraries, and I want to demonstrate this workflow and how to implement on Quantum-ManyBody-MCP. In response to yesterday's talk from Shunyu Yao, he mentioned that we are entering into the second half of AI. The first half is about training LLM. It's more about updating parameters within a large language model. To analog that, it's more like a gene evolution of human species. And the second half is about teaching LLM. So we can expect that in nowadays society, human species are not updating their gene evolutions as before, and they are basically like fixed parameters of LLMs, and they still have some scientific breakthroughs and technology breakthroughs, and they can create some behavioral evolutions among society. So we are actually entering the second half of the AI evolution. So I would say this is from training AI to teaching AI. So how would we actually realize this teaching AI workflow? I want to share some experience I developed during this hackathon that we realized a minimal framework to let AI to self-develop an MCP tool to realize a certain kind of task. And I'm sure this is not the original innovation that happened in our group. There are many research emphasizing this. That I really like to share this experience using this mindset. So there are two important parts to start from. The first one is that you have to create a seed tools that contains like some very basic elementary tools to support some memory manager and language parser. So the memory manager is like providing the AI for some scratch paper to take the history of your program. And the language parser is more like translating your natural language to some basic objects within your Python library. And it doesn't need to be very mature and well developed. It's just some basic tools that you specify for a start. And you ask AI to use these C tools to apply and solve a large task set. And definitely it will fail in the first time, but later on you'll get feedback and try to evolve this MCP2 service to make it better. So in here, I try to let the AI first I wrote down some very basic and simple C tools. They are least quantum systems, basically create a JSON file. And they are create a lattice size and create some Hamiltonian and set some Hilbert space. And those are very simple, and it's not good enough to actually create some concrete analysis of the certain quantum system. But you can ask AI to try to base on these C tools to solve some specific tasks like Ising transition or SSH model or Hubbard model. And it will actually iterate itself until it actually accomplishes those tasks. And within this procedure, it not only revise those C tools, it also create new tools and try to generalize those basic tools to other tasks. For example, here it tries to generalize some basic tools like a compute energy spectrum because it tries to do exact analyzation of a certain Hamiltonian. And then it tries to do a parameter sweep because it wants to scan the parameter and find a phase transition somewhere. So those are the tools that it actually developed itself to really solve those tasks. And here I have a demo for solving the Ising phase transition. Let me see if I can play this video. Yeah. So first question is to create a quantum system for the Ising model. For a 16 side chain with spin half particles. So those C tools that it tries to use are some basic tools I gave the AI. And it tries to create a quantum system and set a Hilbert space and set a Hamiltonian. So basically operating this Python library objects to create a scratch paper and run it. And the second question I asked is that to set the Ising Hamiltonian with JZ equals to 1 and do a transverse field HX sweeping ranging from 0 to 2. And following that, AI can actually use some tools that I never create for it. So it first try to update the Hamiltonian because there's a parameter sweeping process. And after that, it tries to do a parameter sweep, and this parameter sweep is a new tool. It generalizes itself. And also it tries to do some plot XY. I actually don't know what it's trying to do because I didn't write down those tools myself. This is a new tool that AI write and displays numerical result like this. And you can see that by investigating the numerical result, it actually create a concrete and correct result to analyze the Ising model. So there's like a energy gap close and open up again. And also the final question I think I'm trying to ask is that use the same sweep results? Can you create a plot showing the ground state degeneracy as a function of transverse field? And it start to look up to the scratch papers and plot a new figure to demonstrate degeneracy by sweeping the HX. And yeah, you can see that the report is actually correct. You have a degeneracy drop from 2 to 1 by increasing the transversalizing field. And here's a numerical result from 2 to 1. Yeah, so basically this is a very small demo of this self-evolving system. And now our package is open for trial. So it supports different type of lattice types, and you can select one of them to run a real analysis, and you can try some Hamiltonian interactions, and you can specify which is, you can try fermions, bosons, and spins. And you can also download it and clone it directly on your local laptop and try to evolve yourself based on your tasks and push it back to our open source repo. Yeah, thank you.
That it evolved. Like when I look at the video, it looks like it's already using.
Yeah. The video is mature, like after the evolving. So in the evolving process, actually you can actually use multiple ways to do that. My way is that you can basically let cursor to take over the terminal, and you can let cursor to install the MCP and try to run MCP on cursor AI, and then it will get some feedback from the chat box, and then read the feedback and then update the MCP code itself, and then iterate this process. Or you can maybe do it on Lucene and copy paste the response from Lucene to cursor and let cursor to update the MCP code. There are many ways to let it run by itself. Yeah.
You can describe a bit more about the scratch pad or memory manager here.
Oh yeah, so I think I'm trying to do some high concept level to illustrate that. But the thing I do here is that the scratch paper is basically a JSON file manager to write down what kind of particle system you're trying to analyze. Maybe it's a fermion or boson, and it actually correlated to an object to the Python library you're trying to use. We are trying to use the netkit Python library. So using this library, you can actually call a function called set Hilbert space and say it's a fermion, and then can run this code on Python. And you can have many other ways to create this scratch paper. So I think the good part of having a memory manager is that you can at some point close the app, right? Close the AI and then save your result. And maybe you want to send it over to another colleague to start it over again. And somewhere in the future, you want to redo this research and you want to put it up and do something else. Thank you.